The binomial distribution is very useful in many business situations, as indicated in examples and applications presented in this previous section. However, as we pointed out, there are several requirements it must hold before we can use a binomial distribution to determine probabilities. If those conditions are not satisfied, there may be other theoretical probability distributions that could be employed. In this section, we introduce two other very useful discrete probability distributions, the Poisson distribution and the hypergeometric distribution. When using the binomial distribution, we must be able to count the number of successes and the number of failures. Although in many situations you may be able to count the number of successes, you often cannot count the number of failures. If the total number of possible outcomes cannot be determined, the binomial distribution cannot be applied. In these cases, you may be able to use the Poisson distribution. The Poisson distribution describes a process that extends over time, space, or any well-defined unit of inspection. The outcomes of interest, such as emergency calls or potholes, occur at random, and we count the number of outcomes that occur in a given segment of time or space. We might count the number of emergency calls in a 1-hour period, or the number of potholes in a 2-mile stretch. As we did with the binomial distribution, we will call these outcomes successes, even though, like potholes, they may be undesirable. Possible outcomes are integers, 0, 1, 2, and so on, and we'd like to know the probability of each of these values. We can use the Poisson probability distribution to answer these questions if we make the following assumptions. We know lambda, the average number of successes in one segment. The probability of x successes in a segment is the same for all segments of the same size. What happens in one segment has no influence on any non-overlapping segment. And finally, we imagine dividing time or space into tiny subsegments. Then the chance of more than one success in a subsegment is negligible, and the chance of exactly one success in a tiny subsegment of length t is lambda t. Once lambda has been determined, we can calculate the average occurrence rate for any number of segments. Although the Poisson distribution is often used to describe situations such as the number of customers who arrive at an emergency hospital room per hour, or the number of calls Hewlett-Packard LaserJet Printer Service Center receives in a 30-minute period, the segments need not be time intervals. Poisson distributions are used to describe such random variables as the number of knots in the sheets of plywood or the number of contaminants in a gallon of lake water. The segment would be the sheet of plywood and the gallon of water. Another important point is lambda times t, the average number of t segment, is not necessarily the number we will see if we observe the process for t segment. The actual arrivals will form the distribution with an expected value, or mean, equal to lambda times t. Once lambda and t have been specified, the probability for any discrete value in the Poisson distribution is found using the Poisson probability distribution equation. It should be noted that the standard deviation of the Poisson distribution is simply the square root of the mean. Therefore, if you're working with a Poisson process, reducing the mean will also reduce the variability. In this example, a study conducted at Whole Foods shows that the average number of arrivals to the checkout section of the store per hour is 16. Further, the distribution for the number of arrivals is considered to be Poisson distributed. For example, we can find the probability of x equals 12 customers in 1 hour, where t equals 1. As was the case with the binomial distribution, a table of probabilities exists for the Poisson distribution. The Poisson table shows the cumulative probabilities for x or fewer occurrences for different lambda t values. And although the binomial and Poisson distributions are very useful in many business situations, they both require that trials be independent. For instance, in binomial applications, the probability of a success in one trial must be the same as the probability of a success in another trial. Although there are certainly times when this assumption can be satisfied, or at least approximated, in instances in which the population is fairly small and we are sampling without replacement, the condition of independence will not hold. In cases in which the sample is large relative to the size of the population, a discrete probability distribution called the hypergeometric distribution is the correct distribution for computing probabilities for the random variable of interest. The hypergeometric distribution is formed by the ratio of the number of ways an event of interest can occur over the total number of ways any event can occur. Here the sample is taken without replacement and the trials are dependent. The probability changes from trial to trial. As we saw earlier, we use combinations to form the equation for computing probabilities for the hypergeometric distribution. When each trial has two possible outcomes, hypergeometric probabilities are computed using the hypergeometric distribution equation. Notice that the numerator is the product of the number of ways you can select successes in a random sample out of the successes in the population, and the number of ways you can select failures in a sample from the failures in the population. The denominator in the equation is the number of ways the sample can be selected from the population. We can use the equation to determine the probability that 2 of the 3 selected light bulbs are defective. Here the sample and population size are both 10. The number of successes in the population is 4, and the number of successes in the sample is 2. We see that there's a 30% chance that 2 out of the 3 selected light bulbs are defective. Now go ahead and open Excel file poolball and answer the following questions. To determine the number of scratches in the sample, we can simply take the sum of the scratches column. As you can see, it shows that we have 8 scratches in the sample. Lambda in this problem would be 1, and the segment size t would simply be the 48 balls divided by our sample of 16, and the expected number, lambda times t, would simply be our 3 times 1. Here are 2 additional questions. So we can also determine the probability that there would be at least as many scratches observed per set of pocket billiard balls if sticks and stones has met its goal. Similar to before, to calculate the number of having 8 or more scratches, we'll take the complement. We'll begin by determining the probability x is less than or equal to 7. Here our x value will be 7. The mean is simply lambda times t, and we would like cumulative, since we would like all values up to and including 7. And to find the probability of having 8 or more, we'll take the complement of the previous result. So as you can see, it appears that the goal has not been met.